So the atmosphere is basically the fluid, the gaseous fluid envelope that surrounds the Earth. And it is very dynamic. And being a fluid, a lot of times we think of fluids as liquids, but gases, of course, exist in a fluid mixture as well, and that's what our atmosphere is. The atmosphere does lots of different things. It helps to chemically support life, because if you think about some of the different components that exist in the atmosphere, such as carbon and nitrogen and oxygen, they all play an essential role in the functioning of life on our planet. Also, the atmosphere helps to trap energy that radiates from the sun or that radiates from the earth. So it has this ability to do that as well as also store moisture. So the atmosphere plays a very dynamic role in shaping the planet itself, but also supporting life on our planet. The early atmosphere, if we go back 4 billion years in time, the early atmosphere was drastically different than the composition of the atmosphere today. So the atmosphere essentially formed as eruptions from our planet. Our early cooling planet occurred, and you just have to picture, tons and tons of basically volcanic activity occurring with our planet, but also outside forces, comets and meteorites striking the planet would have affected the composition of the atmosphere. The early atmosphere was essentially made up of, there was water vapor, methane, carbon dioxide, ammonia, nitrogen-containing compounds, argon, various acidic compounds like hydrochloric acid, sulfuric acid. But one thing that is very important to realize is there was no elemental oxygen, essentially not much atmospheric oxygen. The oxygen that would have existed in the earliest atmosphere probably would have formed as ultraviolet light struck water vapor, splitting water apart, forming to some degree some oxygen in the atmosphere, but certainly not the levels of oxygen that we see today. Now, oxygen did start to form long ago, billions of years ago. In fact, oxygen started to increase in the atmosphere around 2.5 to 1.5 billion years ago, because of the activity of cyanobacteria. Cyanobacteria is thought that occurred maybe around 3 billion years ago. And cyanobacteria, commonly called blue-green algae, is a type of prokaryotic organism, bacterial life forms. And cyanobacteria has the ability to do a couple of things. In regard to oxygen, cyanobacteria produces oxygen because cyanobacteria is a form of algae, prokaryotic algae, that captures carbon dioxide and uses water vapor to produce organic compounds, sugars essentially, and also liberates or produces oxygen as a consequence of this metabolic process. So cyanobacteria, both in single-celled form and colonial form, greatly affected the composition of the atmosphere early on in life's history, but also affected the types of organisms that existed on our planet, because prior to the appearance of cyanobacteria, all life on this planet would have been anaerobic life forms, those types of life forms that thrive in the absence of oxygen. With the appearance of cyanobacteria, there was basically a regime change with life forms on this planet. So that was a drastic change. Also, many forms of cyanobacteria also affected the nitrogen cycle. Nitrogen, along with other types of bacteria, can be fixed and utilized by bacteria, and so that played an important role in the formation of organic compounds that included nitrogen in them, but also was involved in the nitrogen cycle on our planet as well. The importance of oxygen on our planet, if you think about it, allowed or afforded for organisms with higher metabolic rates. I mean, we undergo cellular respiration or aerobic respiration, and it provides us with a great deal of energy. Oxygen is used as a final acceptor of electrons in the metabolic process of breaking down organic materials, especially molecules like glucose. And so the oxygen that built up did greatly affect organisms on this planet. Now, the oxygen levels throughout time has sort of wildly oscillated. If we even look at the past few 100 million years, oxygen levels have been anywhere from as low as 10% up to 25%. Currently, we run around 21% oxygen in our atmosphere. The carbon cycle also is affected by life and other processes on this planet. So there's carbon sequestration that can occur in the oceans. Oceans are very big and plays a big role in the carbon cycling in the atmosphere. So as carbon dioxide, for example, dissolves in water, carbonic acid forms. Carbon can also, like I said, be taken in by photoautotrophic organisms like cyanobacteria or plants or eukaryotic algae. So many of these components in the atmosphere, maybe this is a drive home point here, many of these compounds that exist in the atmosphere cycle through various earth processes and oftentimes includes life processes, living organisms like nitrogen and like carbon. Today's atmosphere is mainly made up of nitrogen, N2, atmospheric nitrogen, a diatomic molecule. About 79% of the atmosphere is nitrogen. The remaining biggest chunk is oxygen at 21%, like I just mentioned. But then there are other trace amounts of carbon dioxide, methane, argon, and other nitrogen-containing compounds like nitrous oxides or make up a small component of the atmosphere. The greenhouse effect is mentioned, and many people get the greenhouse effect kind of confused with ozone. Now, ozone does exist. It exists in the troposphere as sort of a contaminant or pollutant associated with a lot of human activities. You find heavy ozone layers around cities, that kind of thing. Comes out of the ends of tailpipes, or when we burn fossil fuels or do other activities, we can create or produce ozone. But ozone exists in the lower stratosphere as a consequence of infrared radiation or striking oxygen molecules and splitting them apart, producing oxygen radicals that can then recombine with O2, forming O3. And so it helps to shield us from ultraviolet light and protect us. It's sort of a protective shield around the planet, but essentially doesn't play a big part in the greenhouse effect, except for the tropospheric ozone, like I was talking about. It acts as a greenhouse gas in the lower atmosphere. But the greenhouse effect occurs when heat from the sun or radiation from the sun strikes our planet. It comes in many different forms, from X-rays, gamma rays, ultraviolet light, visible light, infrared radiation. All this is moving to us from the sun in the form of photons, which have the sort of the properties of a particle, massless particle, but move in a wave-like fashion. So the planet, light strikes our planet, visible light strikes our planet. It allows for the photosynthetic organisms to do their thing. Visible light can be absorbed or reflected back out. If there's a white surface like a sheet of ice or snow, it may be just reflected back out. And so visible light can move back out to space. But also, visible light can strike a darker colored surface or heat up a surface, and then the energy moves back out into the atmosphere as heat or infrared radiation. That infrared radiation interacts with many organic compounds such as carbon dioxide and methane, nitrous oxide, water vapor, and many other organics. What happens when infrared radiation strikes these molecules, it specifically interacts with them, causing the bonds to stretch, and it excites the molecules where they re-radiate that energy, disperse that energy into the lower atmosphere where most of these molecules occur. That's the heat trapping capacity of the atmosphere. That is the greenhouse effect. It's kind of like, and I've seen the analogy drawn between visible light passing through the windshield of a car, heating up the interior surface of the car, and as that energy re-radiates back out in a slightly lower energy form as heat, it heats up the car and can be trapped by the windshield. Same kind of thing is essentially the same kind of thing is happening with the molecules in the atmosphere acting as greenhouse gases. There are 4 basic thermal layers associated with the atmosphere. The lowest one is called the troposphere. It extends up about 15 kilometers. This is where we really see our weather. The temperature decreases as it approaches the next layer, the stratosphere, as you increase in altitude. With the stratosphere, of course, this is where we associate the ozone layer. The stratosphere extends up maybe 50 kilometers in height. The temperature increases with altitude in the stratosphere, so it's a little opposite of the troposphere. The mesosphere is the coldest, and the temperature decreases with altitude. So the farther you go up in the mesosphere, the colder it gets, and that extends up to maybe 80 kilometers in height. And then the thermosphere, which is it gets the warmest. The thermosphere, the temperature increases with altitude in the thermosphere, so it's sort of a back and forth kind of thing with the temperature increasing and decreasing. With the thermosphere, temperatures reach up to almost 90 degrees Celsius at the upper limits of the thermosphere. Also, the ionosphere is associated with the thermosphere. Air pressure is considered the force, or is the force exerted by the weight of the overlaying air. Air pressure decreases smoothly with altitude as you go up. The fluid air is highly compressible. About 50% of the atmosphere, the molecules in the atmosphere exist maybe only about 5 kilometers up. And a barometer is an instrument that can measure air pressure. Moisture in the atmosphere. When dew point, which is a measurement of essentially this aspect of moisture, is when the number of molecules that evaporate equals the number of water molecules that condense when the water is vapor saturated. Relative humidity is the amount of water vapor in an undersaturated air, and is considered the relative humidity. Temperature, keep in mind, exerts a strong control over water vapor and the capacity of air concerning water vapor. Relative humidity can be changed either by the addition of water vapor or by a change in the temperature. When air is compressed, this is something to really fundamental sort of thing. When air is compressed on a planet when air is compressed, it warms. When air warms, it rises. As air rises and expands, it cools. As that air cools, it descends. But as it descends, the air pressure increases and it compresses and warms the air, and once again it rises. So there's sort of a cyclical process. Now it's going to be interplayed with various factors, topography on the planet, and sun's radiation and those kinds of things. But that's basically what happens. Warm air expands and cools. As it expands and cools, then it will drop, and so it's a cyclical process. Clouds are visible aggregates of minute droplets suspended in the air. They can be either ice crystals or basically aerosols that water can condense around. There are 4 principal reasons for upward movement of air leading to the formation of clouds. One is warm, low-density air rises. And if conditions are right, clouds will form. The frontal boundaries of 2 air masses coming together, one cooler, one warmer, can force one air mass above the other. Orographic is flowing air is forced upward because of a land feature, because of the topography of the land. And convergence, where 2 air masses come together and both of them move in an upward motion, sort of like a column of air rising. When the dew point is reached, 1 or 2 things will happen, and water will condense. And so it can condense as ice crystals in forming clouds, or the nucleation process can involve an aerosol particle, a minute particle that water will condensate around. Both of them are basically the same. Either one is going to be an ice crystal or a minute particle in which that nucleation process can occur, with the water vapor condensing around that particle. There are different cloud shapes mentioned. Cumulus is puffy individual clouds with a very flat surface where condensation, sort of the condensation limit there. Stratus, these are sheets that are spread out very laterally. Cirrus are the highest of clouds, are very wispy, involving ice crystallization. And nimbus, these are water saturated rain clouds. Lastly, there is a heavy anthropogenic effect occurring with our atmosphere now. The influence that human beings have had on the planet. We've done a lot of things that have changed the conditions of the atmosphere. We've dusted up the atmosphere. So there's a lot of particulate matter in the atmosphere due to human activities, the anthropogenic effect, human-caused effect, and change with the atmosphere. We've clear-cut many forests. Our modern day agriculture has had a big influence on the atmosphere. Many of the pollutants that come from tailpipes and the building of complex cities and just human activities in general. We've put a lot of different aerosols up into the atmosphere, and some of them being carbon dioxide and methane that have actually affected the warming capacity of the atmosphere. This is called global warming or climate change. And so we've affected it that way, but also just taking into consideration the carbon dioxide that we've put in the atmosphere has not only changed the composition of the atmosphere, but we're also changing the composition of the oceans. The pH levels of the oceans are actually decreasing because of the amount of carbon dioxide in the atmosphere dissolving into the oceans. And so more carbonic acid forms in the ocean, causes the oceans to become lower in pH. But there's many different factors that have been human caused concerning the changing composition of the atmosphere.